Today, I will be presenting our work, MemorySeg, Online LiDAR Semantic Segmentation with a Latent Memory. LiDAR sweeps are typically captured as a continuous stream of data, where every fraction of a second a new point cloud is available. Despite this fact, traditional LiDAR semantic segmentation methods usually rely on a single LiDAR sweep, or a sliding window approach, where a small set of pass frames is processed independently at every time step. These traditional approaches have several limitations. First, they discard previous observations and require the model to start from scratch at every time step, failing to capture the potential of temporal reasoning over a long horizon. Secondly, reasoning about a single frame suffers from the sparsity of the observations, particularly at long range. Moreover, the network may struggle with occluded regions since there are no observations available. Prior works have attempted a recurrent segmentation architecture in RangeView, which uses previous observations as memory. However, RangeView memory has limitations. The range view of the scene changes drastically as the ego vehicle moves due to changes in perspective. As a result, the memory could be dominated by nearby objects. Occlusion can be particularly challenging as the occluder now occupies the same spatial region in RangeView that was previously describing the occluded object. Therefore, it limits the usefulness of the memory. This motivates our approach, MemorySeg, a novel online LiDAR semantic segmentation framework that recurrently updates a sparse 3D latent memory as new observations are received, efficiently and effectively accumulating geometric information as well as learned semantic embeddings from past observations. In contrast to RV, 3D is a metric space where the distances between points are preserved regardless of the viewpoint change. It allocates equal representation power to objects regardless of their relative distance to the ego vehicle, which enables easy understanding of motion. Moreover, previously observed regions that are currently occluded can be remembered in the memory, as the occluder and occluded objects occupy different 3D regions. The inference of MemorySeg follows a three-step process that is repeated every time a new LiDAR sweep is available. First, the encoder takes in the most recent LiDAR point cloud at current time t and extracts observation embeddings. Then, the latent memory is updated, taking into account its previous state and the current observation embeddings. Finally, the semantic predictions are decoded by combining the encoder features and the updated embeddings from the latent memory. The process is repeated in a similar manner for subsequent time steps. Our results are evaluated on 3 public datasets. Each dataset was collected with a different sensor and in different geographical regions. To assess the effectiveness of the learned latent memory, we compare against our encoder and decoder without the memory update module, as the single frame baseline. We evaluate the model performance using the mean IOU metric, plotted in relation to the distance from the LiDAR sensor. Our proposed network consistently outperforms the single frame baseline in all areas of the new scenes dataset, with the most significant improvement observed in the long-range region, where points are much sparser and more difficult to contextualize. We observe a similar trend in Semantic Kitty and PandaSet. These results showcase the usefulness of the 3D latent memory in providing better contextualization of sparse observations from a single frame. MemorySeg outperforms all previously published works on all benchmarks in terms of mean IOU, demonstrating its ability to generalize across different LiDAR sensors and geographical regions. To further demonstrate the usefulness of the latent memory, we plot the visualization on the left-hand side, where PCA is applied to reduce the embedding dimension to RGB. On the right side, we display the prediction generated by our network on the single scan. It is difficult to identify objects in a single scan due to the lack of semantic information and sparse observations, and occluded regions have no observations at all. In contrast, our latent memory is much denser, contains rich semantics that help separate different classes, and provides contextual details in occluded areas. Now we show a qualitative comparison with our baselines. Please focus your attention on a vehicle parked vertically, colored in dark blue, that is approaching from the top right. Initially, our approach fails to segment the object correctly. However, as the ego vehicle moves forward, the latent memory accumulates and refines the embeddings with new observations. MemorySeg consistently segments the object correctly without any flickering, even as the ego vehicle moves further away from the object. In contrast, the 2 baselines at the bottom fail to recognize the parked vehicle, and the segmentation results fluctuate over time. In conclusion, we introduced MemorySeg, a state-of-the-art LiDAR semantic segmentation model which retains information from the past through a sparse 3D latent memory. The memory helps to contextualize objects in areas with sparse observations. Our approach outperforms all published LiDAR-based methods on Semantic Kitty, NewScenes, and PandaSet. Thanks for your attention.